Hello students, in this session we are going to consider Cauchy's general principle and algebra of sequences. So here first I will state the theorem that is called as Cauchy's general principle. The theorem says that a necessary and sufficient condition for the convergence of a sequence Sn, for the convergence of the sequence Sn is that for epsilon greater than 0, there exists a positive integer m such that modulus of Sn plus p minus Sn is less than epsilon for every n greater than or equal to m and p greater than or equal to 1. So note the difference between the definition of convergent of a sequence and Cauchy's principle. So in convergence we have Sn minus L less than epsilon. So it is said to be a Cauchy sequence, and that Cauchy's general principle says that a necessary and sufficient condition for the convergence of a sequence, that is, if Sn plus p, n plus p clearly greater than n. So the terms difference is less than epsilon for every n greater than or equal to m and p greater than or equal to 1. So here first we prove this theorem. So now first we assume that Sn converges to L, that is we show that the condition is necessary, that is we assume that Sn converges. So assume that Sn converges to L. So by definition there exists an epsilon greater than 0 such that for epsilon greater than 0 there exists a positive integer m such that modulus of Sn minus L is less than epsilon for every n greater than or equal to m, where epsilon is a positive integer, and for our convenience I will take it as epsilon by 2. So this is our assumption that Sn converges. Now if p is greater than 1, p greater than or equal to 1, it is given. So n plus p is clearly greater than or equal to, it is greater than n, and n is greater than or equal to m. So modulus of Sn plus p minus L is also less than epsilon by 2 for every n greater than or equal to m. Why is this? If this n is greater than or equal to m, then this is true. So in place of n we have n plus p now, that n plus p is greater than or equal to m now. So if n is greater than m, we write n here. Now n plus p is greater than m, therefore this is true for Sn plus p. So this is also less than epsilon by 2, and for every n greater than or equal to m and p greater than or equal to 1. So now I will consider the difference modulus of Sn plus p minus Sn, that is this one. We have to show that this is less than epsilon now. So Sn plus p, I will add and subtract L now. So it can be written as minus L plus L minus Sn. Then group the terms like this. This is Sn plus p minus L, one term. Another term is minus of Sn minus L. This L minus Sn, this is taken here, can be written as minus of Sn minus L. Now this is less than or equal to modulus of Sn plus p minus L plus modulus of Sn minus L, because mod x minus y is less than mod x plus mod y. But by our assumption, this is less than epsilon by 2 and this is also less than epsilon by 2. So this is less than epsilon for every n greater than or equal to m and p greater than or equal to 1. So this proves that Sn plus P minus Sn is less than epsilon. So this proves the necessary condition. So if the sequence converges, the convergence of the sequence is necessary for this condition. So that is proved now. Now we shall prove the converse. So that is, we show that the condition is sufficient. The condition is sufficient. So for that, first we have to assume that modulus of Sn plus P minus Sn is less than epsilon. That is, if this condition is true for every n greater than or equal to m and p greater than or equal to 1, we have to show that now Sn is, we have to prove that Sn is convergent. We know that every bounded sequence is convergent. Therefore, to prove that it is convergent, we show that Sn is bounded. So, for that, first we assume that epsilon equal to 1. Let us take epsilon equal to 1. Then, from this expression, modulus of Sn plus P minus Sn is less than 1. For every n greater than or equal to any m, I will take it as m naught, and p greater than or equal to 1. So what happens if n is equal to m naught? When n is equal to m naught, this expression takes the form S m naught plus p minus S m naught is less than 1. This is less than 1 for every p greater than or equal to 1. So if you expand this, this is nothing but S m naught plus p minus Sm naught is less than 1 and greater than or equal to minus 1. This is less than 1, greater than or equal to minus 1, and this is for every n greater than or equal to m naught. So we can now greater than or equal to, so I will keep Sm naught plus p in the middle. It is less than or equal to Sm naught plus 1 and greater than or equal to Sm naught. This is less than 1, strictly less than 1. So we can consider only less than here. So greater than Sm naught, add Sm naught here, then plus minus 1. So from this, Sm naught lie between Sm naught minus 1 and Sm naught plus 1. This is true for p greater than or equal to 1. Now, we assume that among the elements S1, S2, etc., that is, we assume that small g is minimum of the numbers S1, S2, S3, etc. up to Sm0 minus 1, this expression, and S another number is Sm0 minus 1, separate from this. This is suffix minus 1, this one. This expression is Sm0 minus 1. This suffix is m0 minus 1. And we assume that capital G is maximum of this S1, S2, S3, etc. up to the same thing here, Sm0 minus 1 here, comma, Sm0 this term plus 1. So let us see what is the assumption and how it helps to prove the theorem. So this means that all Sn, the terms of the sequence, are greater than or equal to small g and less than or equal to capital G. Why is this? Because the small g is minimum of S1, S2, etc. So if S1 is minimum, then all the terms are Sn is greater than or equal to, if G is S1, then Sn is greater than or equal to S1. All the terms are greater than or equal to S1. And if capital G is maximum of this, so for example, it is equal to this, Sm0 plus S1. Then what happens? According to the definition, capital G is maximum of this. So maximum value of Sn is this one, means it is other terms are less than Sm naught plus 1. That is nothing but Sn less than G. So this means that Sn is bounded. So if you assume like this proves that Sn is bounded. So now we apply Bolzano-Weierstrass theorem that says that every bounded sequence, that is, if Sn is a bounded sequence, it has at least one limit point. So say L, it has at least one limit point. A very bounded sequence has at least one limit point. So take Sn limit point as L. And now by definition, we show that Sn is the limit point of L, but we show that Sn converges to L. So Sn converges to L. To prove that the condition is sufficient, we have to show that if this condition is true, Sn is convergent. So for that, it is not enough to show that it is bounded. We show that it is bounded and it has a unique limit point, or we show that L is the limit point of the sequence. The Sn converges to that limit point L. So now for this, uh, we assume that for epsilon greater than 0, we use the condition that L is the limit point. So for epsilon greater than 0, there exists a positive integer m such that modulus of Sn plus p minus Sn, this condition is less than epsilon we have already. So now I will take it is less than epsilon by 3 for our convenience for n greater than or equal to m and p greater than or equal to 1, because this condition is always true. And now when n equal to m, what happens? If n equal to m, this is Sm plus p minus Sm, and this is less than epsilon by 3 for same condition n greater than or equal to m and p greater than or equal to 1. Now we have one more thing, that L is the limit point of Sn. So L is the limit point of Sn means there is a number m1. There exists a number m1. We can assume that it is greater than m such that modulus of Sm1 minus L is less than epsilon by 3, because we usually take n greater than or equal to m, and definition of Sn, L is a limit point of Sn means Sn minus L is less than epsilon by 3. But in place of n, I am taking m1 now. So Sm1 minus L is less than epsilon by 3. And here we have another relation like this. And one more condition we can take for m1 greater than m. If m1 greater than m, use this condition. N plus p is greater than Sn, we can use this. So use this condition for m1 and m, so that because m1 greater than m, so another condition is Sm1 minus Sm is less than epsilon by 3 for m1 greater than m. So we have now three conditions, this one and this one. Add all them, we get Sm plus p minus Sm, and here plus Sm minus 1 minus L, and then this is Sm1 minus Sm. So we can consider this as Sm plus p minus L, and other term vanishes. So I will show it. That is, consider now Sm plus p minus L. So this can be written as Sm plus p. First add and subtract Sm minus Sm, then add Sm, and then subtract Sm1 and add Sm1, and these are added and subtracted. Finally, minus L is there. So this is less than or equal to Sm plus P minus Sm, one term, plus modulus of Sm1 minus Sm and plus modulus of Sm minus L. These two terms minus of each other, so minus of Sm minus 1 minus Sm, but while taking modulus it becomes plus. These two are clubbed together and Sm minus L is written here and these two terms are written here. Now we can see that each one is less than epsilon by 3 from the previous step. So once again I will show it. Sm plus P minus Sn here, Sm. Then Sm1 minus Sm1 minus Sm, this term. And then next one is Sm1 minus L. So we can see that it is the last term. So this is Sm1 actually. Sm1 is Sm1 minus L. So now we can see that, yes, this is the difference between these two, not these two. So this is the last term and these two terms here and first two terms here, they are taken as it is. So this is 3 times epsilon by 3, it is less than epsilon for every n greater than or equal to m. So this proves that the sequence Sm plus P minus L, or it is same as Sn, converges to L. So this proves that if this condition mod Sn plus P minus Sn is less than epsilon for every n greater than or equal to m and P greater than or equal to 1, then the sequence converges. So now we define a Cauchy sequence. Using this principle, we define the word Cauchy sequence. A sequence Sn is called a Cauchy sequence or a fundamental sequence if it satisfies the condition if for epsilon greater than 0 there exists a positive integer m such that modulus of the same thing Sn plus P minus Sn is less than epsilon for every n greater than or equal to m and P greater than or equal to 1. So this condition can also be written like this. Anyway, these are two integers in such a way that this is greater than this. So in place of this, you can take any integer n1, here another one, not another number n2. So only thing is n1 greater than or equal to n2 because n plus p is greater than n. So this expression, this condition, whatever we proved in the theorem, this is nothing but the definition of a Cauchy sequence. So we can also write Cauchy sequence definition like this. If Sn1 minus Sn2 is less than epsilon for every n greater than or equal to m, also both n1 and n2 greater than or equal to m. And now we have a very important result about Cauchy sequence. So that result says that a sequence is convergent. A sequence is convergent if and only if it is a Cauchy sequence. Because the definition of Cauchy sequence is nothing but the necessary and sufficient condition of the above theorem. So if that is that definition of Cauchy sequence, so we have seen that it is convergent. If it satisfies that condition, it is convergent. So this is a very important theorem about Cauchy sequence. A sequence is convergent if and only if it is a Cauchy sequence. Now consider some problems. For example, Sn is equal to 1 plus 1 by 2 plus 1 by 3 plus etc. plus 1 by n. So we show that this sequence cannot converge. So for this, it cannot converge. So for this, just now we proved Cauchy's general principle. So if it is true, it converges. So if it is not true, it cannot converge. So we show that now Cauchy's general principle fails here. So for that I will take now epsilon equal to half and take n equal to m and p also equal to m. So in Cauchy's general principle we have S n1, I will take it as 2m minus S another n2, I will take it as m. This is less than epsilon. Epsilon means half here. For every n1 greater than n2 here. So we know that 2m greater than or equal to m, and for every n greater than or equal to m also. So here we have chosen n equal to m. So this means that S2m, what is S2m? This is Sn. So S2m is 1 plus 1 by 2 plus 1 by 3 plus etc. plus S2m is 1 by, last term is 2m means m plus m. So before S2m we will have 1 by m, and then the last term is 1 by 2m. So up to 1 by 2m it is S2m. So how it reaches 1 by m, then 1 by m plus 1 and etc. up to 1 by m plus m. Similarly minus Sm. So Sm is 1 plus 1 by 2 plus 1 by 3 plus etc. plus 1 by n. So here this is less than which number we shall see. So this is less than half for every 2m greater than or equal to m, the difference, but we will see what is the difference. So up to 1 by m it cancels, this is Sm. So these term cancels and we are left with modulus of 1 by m plus 1 plus 1 by m plus 2 plus etc. plus 1 by 2m. But we can see that each number is greater than 1 by 2m because m plus 1 is less than m plus m. M plus 1. Similarly, m plus 2 is also less than m plus m, or m plus 1 is less than 2m. M plus 2 is also less than 2m. But if you take the reciprocal, m is a positive integer, 1 by m plus 1 is greater than 1 by 2m. Similarly, 1 by m plus 2 is greater than 1 by 2m, like this. So each term is now greater than 1 by 2m. So 1 by 2m, 1 by 2m, start from 1, 2, etc. up to m. So here there are m terms. So these are m terms. So 1 by 2m is added m times, hence it is m into 1 by 2m. But m into 1 by 2m means it is half. So this expression is greater than half. But Cauchy's general principle, if you apply, we should get less than half. So we should get it as less than half. So here we got it greater than half. This means that is if it satisfies Cauchy's general principle, it should be less than half. But we got it greater than half. This means that Cauchy's principle fails here. So the sequence cannot converge. Next we consider algebra of sequences. So here it is very simple. We take some sequences, nth term, an, bn, etc. So if Sn is sum of two sequences, suppose Sn is an plus bn, or an minus bn, or an by bn, or an into bn, then these are the nth terms of the sequence. Then nth terms of Sn is here an plus bn, nth term of Sn is an minus bn, etc. So a theorem says that if an and bn are two sequences such that limit n tending to infinity an is a and limit n tending to infinity bn is equal to b, then the theorem says that limit n tending to infinity an plus bn is limit n tend into infinity an plus limit n tend into infinity bn, it is a plus b. Similarly, if it is minus, minus here. In the same way, another property is about multiplication. Limit n tending to infinity an into bn is limit of an into limit of bn, and this is nothing but a into b. And the proof is very simple. So to prove that, first one, given that limit n tend into infinity an is a and limit n tend into infinity bn equal to b. So by definition, this implies there exists a positive integer m1 such that mod an minus a is less than epsilon for every epsilon greater than 0 and n greater than or equal to m1. Similarly, this implies that mod bn minus p is less than epsilon for every n greater than or equal to m2. Now I will choose m as maximum of these two numbers m1 and m2. Maximum of m1 and m2. So here the first condition says that it is less than epsilon for every n greater than or equal to m1, where m1 is a positive number and m2 is also positive number, and epsilon is greater than 0. So now I have to prove that an plus bn converges to a plus b. So consider the difference. This is Sn and this is now L. So consider the difference of Sn and L. So an plus bn minus a plus b can be written as an minus a plus bn minus b. So this is less than or equal to modulus of an minus a plus modulus of bn minus b. And we have seen that this is less than epsilon by 2 and this is also less than epsilon by 2, which is less than epsilon for every, this is for every n greater than or equal to m1, and second one is true for every n greater than or equal to m2. So both together are true for every n greater than or equal to m, because m is maximum of m1 and m2. So if m is equal to m1, n is greater than or equal to m1, which is true. And if m is m2, then n is greater than or equal to m2. So it is maximum of m1 and m2. Anyway, it is greater than or equal to that maximum value. So this is true for n greater than or equal to m, and this means that this plus an plus bn converges to a plus b. Similarly, if you consider minus here, then it takes the form this as minus an, this term is now minus bn, so here minus, instead of plus we have minus here, and this is minus plus minus bn plus b, it is minus of bn minus c. So anyway, this is same, because mod x minus y is less than or equal to mod x plus mod y. So same thing is true for this also. So an minus bn converges to a minus b. Then one more thing is about the product. So here an and bn, given that they are convergent. So they are convergent means they are bounded. So we use the definition of bounded sequence. So there exists a positive real number k1 and k2. For a1 there is a positive number k1 and another k2 such that an, mod an is less than or equal to k1 and mod bn is less than or equal to k2. This is for every n. For all terms of the sequence are less than a particular number if it is bounded. So now we have to show that an bn converges to ab, sn converges to l. So consider the difference sn minus l. an bn minus ab. So this can be written as an bn. In between I will add and subtract a term, that is I will add plus a and b and subtract a and b and then last term as it is. So this can be written as an bn minus an into b. I will group these two terms together. So it is an into bn minus b plus among these two terms I will take b outside, b into an minus a. So here we can see that this is less than or equal to mod an into mod this. But mod an is less than or equal to k1. So it is k1 into mod of bn minus b plus mod b into mod an minus a. So take this as equation 1. Now we have a relation that limit, it is given that limit n tending to infinity an equal to a. So applying the definition, mod an minus a is less than epsilon. Actually it is less than epsilon for every n greater than or equal to m1. Similarly, limit n tending to infinity bn is equal to b. This implies mod bn minus b is also less than epsilon for every n greater than or equal to m1. Another number m2. But instead of epsilon, we will take any number such that that expression is positive. So here I will take epsilon divided by, in order to cancel this with b, I will take epsilon by mod b. Because if epsilon is positive, epsilon by mod b is again positive. And here also bn by b, we have to cancel it with k1. I will take it as epsilon by k1 for n greater than or equal to m2. So as in a previous problem, we choose m as maximum of m1 and m2. And now substitute these two in equation 1. We get mod an bn minus ab is less than or equal to k1 into, this is epsilon by k1, this expression bn minus b mod is less than epsilon by k1 plus another one mod b into epsilon by mod epsilon by this expression mod b. Already here we have mod b. And one more thing, I have to choose here not epsilon by 2. Instead of this, I will take epsilon by 2. So k1 cancels, here b1 cancels, epsilon by 2 plus epsilon by 2 is less than epsilon for every n greater than or equal to m. It is once again because n is greater than or equal to m1 and n is greater than or equal to m2. So n is greater than or equal to maximum of m1 and m2, which is m. So this condition proves that A and Bn converges to AB. So this proves the formula. The product A and Bn converges to AB. Thank you.